Hi, this is Geometry, Topic 3, Lesson 4, Classification of Rigid Motions. In the past lessons, we talked about different types of transformations. We started with reflection, and then translation, and then rotation. So in this lesson, you'll be able to identify different rigid motions used to transform two-dimensional shapes. Okay, that means you'll specify a sequence of transformations that will carry a given figure onto another. You will also use geometric descriptions of rigid motions to transform figures. Let's look at critique and explain. I'm just going to highlight that. Two students are trying to determine whether compositions of rigid motions are commutative. Do you remember what commutative property is from Algebra 1? Okay, commutative means in algebra, it doesn't matter if the order changes, like commutative property of multiplication, commutative property of addition and multiplication. We have commutative properties in those operations, right? The order does not matter in those operations. So we're talking about, oh, does the order matter for our compositions of rigid motions? Okay, Paula translates a triangle and then reflects it across a line. When she reflects and then translates, she gets the same image. She concludes that compositions of rigid motions are commutative. Okay. So if you look at her drawings over here, sketches, she's going to translate and then reflect. She's also going to reflect and then translate. So we do end up with the same image for this triangle. Is it really the same? Another student, Keenan, rotates a triangle and then reflects it. Okay, he rotates and then reflects it. When he changes the order of the rigid motions, he gets a different image. He reflects it first and then rotates it. Now he gets different images. He concludes that compositions of rigid motions are not commutative. So part A. Should Paula have used grid paper? Explain. Part B. Do you agree with Paula or with Keenan? Explain. Think about these questions and let's see what you think. Okay. Should Paula have used grid paper? She noticed that her paper is just blank and Keenan used grid paper. So is it better to use a grid paper like that? Well, with grid paper, she would have still found that her compositions are commutative with her reflection and then translating, or translation and then reflecting, right? It doesn't really matter for her. She should have tried several different combinations of rigid motions, not just translation and reflection, right? We have rotation as well. So she should have tried more before drawing a conclusion. So part B, you can agree with Keenan because he gives a counterexample that shows compositions are not always commutative. But is it sometimes commutative? Yes. Just like Paula figured it out, sometimes it is. Sometimes it is commutative, but not always. Okay? So let's record our answers. Okay, so let's think about how rigid motions could be classified. Let's first start off with a theorem 3-3. The composition of two or more rigid motions is a rigid motion, okay? Even if we have 2 or 3 compositions of rigid motions, because they're all rigid motions, they should stay as a rigid motion. Okay, so if we start with the shape Q or ST, and then we do our first transformation, Q prime, R prime, S prime, T prime. And then we perform another transformation and we end up with Q or ST prime primes. And if we know that those two transformations are rigid motions, altogether, they're going to be rigid motion altogether. Okay, together, even if they're combined and even if they're summarized with another transformation. Okay, look at example 1, prove theorem 3-3. We're going to write a paragraph proof. So we're just going to write a bunch of sentences, starting with the given information, writing out the sentences with the correct reasoning, and proving our last statement. Given T and S are rigid motion. Okay, we have T and S as a composition of transformations. Prove that S and T together combined is a rigid motion. Okay, first we're going to let P, Q, and R be any 3 non-collinear points in the pre-image. And you want to show that the length and angle measure are preserved because that's the definition of rigid motion. So it is sufficient to show that PQ is equal to P prime Q prime, P prime prime Q prime prime, and say the measure of angle PQR is equal to the measure of angle P prime prime Q prime prime P prime prime R prime prime. Okay, so our thinking about our plan, our proof is going to be like this. Since T and S are rigid motions, PQ, line PQ should be equal to P prime and Q prime because the definition of rigid motion is to preserve length, right? So this and this should be the same. Because S is also rigid motion, PQ prime should also be equivalent length with PQ prime prime, right? And so, and our angle measures are also preserved. So they're all the same. All right, same angles, same length. So by the transitive property of equality, this angle, the first angle and the last angle should be the same. The first length and the last length should also be the same, which means altogether, T and S combined would also be rigid motion, okay? Because it preserves length and angle measure. So now let's describe how you can use the reasoning used to prove theorem 3-3 to show that the theorem is true when composing 3 rigid motions, okay? Even if you add another rigid motion, is it still going to be a rigid motion altogether combined? Yes, because rigid motion preserves angles and distances, right? So your last, even if you add another rigid motion, it's still going to preserve angle and the side lengths, which means you're still going to end up with the same angle and the same side length with the original pre-image. Okay, can your strategy be extended to include any number of rigid motions? So does it work for n number of rigid motions, not just 2 or 3? Does it work for 5 rigid motions? 10 combination of rigid motions? Yes, it should. With the same logic, if we only use rigid motion, then altogether combined from the first pre-image to the very last image, it should still follow a rigid motion. Okay, so let's record that on our space on the left. Okay, so remember that a rigid motion by definition preserves distance and angle measures. So keep that in mind. Example 2, explore glide reflections. Part A, is there a rigid motion that maps triangle ABC to triangle A prime, B prime, C prime? Got it? So let's see what kind of rigid motions that can map from here to there. You could translate over here, or you could reflect like this, but you have to reflect again, and then you have to rotate. What is the easiest combination? Okay. The angles, look at the angles here. The angles are the same, right? They're the corresponding angles. And then look at the points, look at the locations where they are at. You can reflect. How about reflecting on the y-axis instead of the x-axis, right? And then you can translate it over here. Does that make sense? Okay, so it does matter where you reflect or how much you rotate for reflection and rotation. Okay. Length and angle measure are preserved, so it is a rigid motion. So let's figure out the exact rules for the transformations here. Okay, if you look at, this could be a combination of a reflection and then a translation, but can one transformation explain this? This cannot be one translation, right? Because you have to reflect at some point. What about a rotation? Okay, if you rotate it 180 degrees, you're gonna end up here. Orientation is not preserved, so it's not a rotation. Okay, what about a reflection? If you reflect over y, it should be over here. If you reflect over x, it should be over here. Does it map directly to your image? No. Okay, so it's not a reflection, not a rotation, not a translation. Can you have just one transformation to explain this? No. So part C, what composition of two rigid motions maps triangle ABC to triangle the image? Okay, so now that we know there is not one single transformation that could map the pre-image to the image, we're gonna find a composition of two or more transformations, okay? So just like we talked about it before, we're gonna reflect it across the y-axis or reflect it across this line and then translate your triangle down, okay? If you reflect across the y-axis, you should get a triangle over here, but then you need to translate it down 1, 2, 3, 4, 5 units, okay? And then 1, 2 units to the left. Does that make sense? So yeah, it depends on where you reflect your, the line of reflection, where you reflect at, and then you need to adjust your translation after that, okay? The composition of a reflection followed by a translation in a direction parallel to the line of reflection is a rigid motion called a glide reflection. So if you do this and then you just slide down and it's parallel, this motion is parallel to your line of reflection, that is called the glide reflection. If you reflect across the y-axis and then do a translation from here to there, that is not parallel to your line of reflection. That is not going to be a glide reflection, okay? Only when you have a translation that is horizontal to your line of reflection, that is called a glide reflection, okay? So you reflect it and you just glide it down. Number 2, draw the perpendicular bisector of B to B prime, okay? The line B to B prime. Is that line also the perpendicular bisector of the line A to A prime and C to C prime. Okay. Use your answer to explain why reflection alone can or cannot map triangle ABC to triangle A prime, B prime, C prime. So first, let's draw a perpendicular bisector, B to B prime. Okay. That is a line, perpendicular bisector. Would be starting from the midpoint. Okay. It needs to be perpendicular, 90 degrees. Okay. The perpendicular bisector. And then let's also draw some lines from C to C prime. Okay. And then A to A prime. Wait. Yeah. Okay, your perpendicular bisectors. Is it also perpendicular bisector of, is this perpendicular bisector also perpendicular bisector of the other two lines? No, you have different slopes. You need different perpendicular slopes for these two other lines, right? Those cannot be the same perpendicular bisector angle. So explain why reflection alone cannot or can or cannot map a pre-image to another image for this one. Because in order to reflect the whole image, you need to be able to reflect all the points to the same line of reflection. They're all going to have different line of reflection for your image point, your pre-image points to the image point, right? Okay, you also need to remember that the line of reflection is the perpendicular bisector of the segment connecting an image and its pre-image. So using that information, we just proved that no, that's not going to help using only one reflection. Let's record that. Okay, you can say no, a reflection alone cannot map triangle ABC to triangle ABC primes because all points need to be reflected on the same line of reflection, which is impossible for these images. Let's look at example 3. Find the image of a glide reflection. A digital artist is reproducing a tire tread pattern from a partial tire print from a crime scene by applying a glide reflection. She uses the rule translation of 0 horizontal movement and 0.1 vertical movement upwards, and followed by reflection across the y-axis. Notice that the capital R represents reflection, and the lowercase r represents rotation. Okay, reflection is the bigger one. To generate a pattern, confirm that her rule can be applied to the partial pattern that was taken from the crime scene. Okay, so step 1, you're going to apply the first rigid motion. You're going to first reflect the outlined pre-image across the line x equals 0. Okay, so reflection across the y-axis. Okay, and then you apply the second rigid motion, which is translating the reflection 0.1 unit up. So first you reflect the yellow one so that it becomes a blue one, and then you translate a little bit up. And that is called a glide reflection because you reflected and then move upwards. And this upward movement is parallel to your line of reflection. Okay, the rule appears to map the pieces of the partial pattern onto itself. Okay, also note that the rotation tells you the order in which you should use the transformations. Remember that in the composition T of R, the reflection is performed first. Okay, T of R means T follows after your R. So translation after your reflection. Try number 3, quadrilateral RSTV has vertices, this, and this. Use the rule T of R, which means translation of one unit to the right after you perform reflection across x-axis to graph and label the glide reflection of RSTV. Okay, let's plot the points. We have -1, 2, 3, 2 for R, 0, 1, 2, 3, 4, 5 for S. Okay, T, 1, 2, 3, 4, 1, 2, 3, 4 for T, and 0, -2 for V. Okay. Connect these dots. Okay. So reflection across the x-axis. Let's write the coordinate points. 4, -4, and then 0, 5, and then -3, 2. Do you remember what the rule was for reflecting across x-axis? Your x values stays the same. They stay the same, but your y values are the opposites, right? So your v prime should be 0, +2. Okay, should be the same distance away from your x-axis. Okay, and then that's v prime. T prime should be 4, +4. T, 4, +4. V, 0, +2. R, -3, -2. R prime, -3, -2. And then lastly, what did we not graph? S prime, 0, -5. Okay, that is S prime, 0, -5. And connect all the dots. I know this coordinate graph is not perfect, but if you have a pretty grid line, you can use your grid line like I do, but I'm writing on the screen, so please understand. All right, and then that is your first reflection. That is first transformation, which is reflecting across the x-axis. And then your next your next transformation would be your translation of one unit to the right. So move all your points +1 for your x values. Okay, so your t, that was t prime, right? T prime becomes 5, 4 instead of 4, 4. Okay, and then your S prime becomes S prime becomes 1, -5. So it's over here. And then your R prime becomes -2, -2. Okay, R prime. And then V prime becomes 1, 2. Connect the dots. All right. So please graph them. And label the glide reflection of RSTV. You should have all the coordinate points. Okay. So your final image should be, let's start with R. You have R prime prime as, where's my R? -2, -2. Okay, that's R prime prime. And then S prime prime, 1, -5, T prime prime, 5, 4, and V prime prime, 1, -2. Okay. Since we're combining all these, you can just say, oh, that's R prime, S prime, T prime, V prime for your image, your final image. Okay. All right. So your theorem 3-4 says any rigid motion is either a translation, reflection, rotation, or glide reflection. So if M is a rigid motion, then M is either reflection on line L or translation of X units left or right, Y units up or down, okay? Or it could be a rotation of n degrees at point P, or it could be a combination of a reflection and a translation, okay? You will prove this in a more advanced course, which is not going to be this year, okay? Corollary to theorem 3-4. So corollary means it comes after from theorem. It's like a sub-theorem, okay? Any rigid motion can also be expressed as a composition of reflections. Any rigid motion can be expressed as a composition of reflections. So it could be 2 reflections, 3 reflections, how many numbers of reflections? Any rigid motion, if it's a rigid motion, you could reflect, 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 keep reflecting at different lines to finally get your image. Okay. Example 4, determine a glide reflection. What is the glide reflection? You want to define this transformation as glide reflection that maps your image, pre-image JKL to image JKL prime, prime. So first, you need to know that glide reflection is what? A reflection, and then a translation of the movement that is parallel to your line of reflection. Okay, it needs to be glide reflection. It can't just be any reflection and then a translation, okay? So it needs to have a line of reflection that can give you a glide reflection that you could just slide down over the direction parallel to your line of reflection, okay? So first, think about where you want to reflect it to. You might want to reflect it across y-axis, or you're going to reflect it vertically or horizontally. That's the first problem you're thinking of, okay? If you reflect it at a vertical line, then your triangle is going to look something like this. And is the orientation right? No. So you have to think about horizontal reflection. If you reflect horizontally, your triangle should look like this. Does that look right? Yes. So figure out the reflection, the line of reflection where you could have point J over here so that we can glide over here, right? Just glide to the left, to the right. So find the midpoint between this, your point J that has height of 4. So you want a certain X that has a height of 4, which also your X has to be the same as your pre-image because you're reflecting horizontally, right? So that's the point you want for J. which means because your angles and your distance of the sides are preserved, your L prime should be here, -2, 4. And then your K should have the same rule, right? Should be -2, -1. So what kind of reflection? Where is the line of reflection at? You can draw a line between your points of pre-image to your first image, and then find the midpoint of that. For this one, you can directly count your distance, the vertical distance. 1, 2, 3, 4, 5, 6. What is the midpoint? What is the mid distance of 6? 3. So your midpoint should be over here. And all your midpoints should lie at exactly where? Y equals 1 line, okay? So that is your line of reflection. That is how you figure out your line of reflection. And then you can glide how many units to the right? 1, 2, 3, 4, 5 units to the right. So pick a point and look at your distance between your point to your final image. Okay, so at last, you're gonna write the rule for glide reflection. Remember, you're gonna write T of R, you're gonna write T first because it's gonna be performed later. T of R means you perform translation after reflection. So translation of 5 units to the right would be this. After reflection across line L, which is over here, which is Y equals 1, right? So to be more specific, let's write translation T sub 5, 0 of R sub Y equals 1. Okay, parentheses, and then parentheses again for triangle JKL to end up at JKL prime. Okay, if you don't want to write the next phrase where L is the line Y equals 1, you can just go over and put that information under your reflection. Okay, so let's try number 4. Come back when you're ready. What's the glide reflection that maps each of the following? Okay, first part A, you have a triangle just like we had. Part B, you have a line. Oh, yes. Okay, yeah, lines. Come back when you're ready. All right, look at part A. You have a triangle ABC. You have the coordinate points ABC, and then you have the endpoints, A prime, B prime, C prime. Right? So first, it should help you if you graph them. -3, 1, 2, 3, 4. That's A. And then -4, 2. That's B. C is -1, 1. Okay, that's C. And then finally, you want to end up at -1, 1. And then 1, 1. 2, -1. And -1, -2. Wait, what did I do? Oh, A prime is 1, 1. And that's B prime, and that's C prime. I repeated myself for C. Okay, so how can you glide? How can you reflect so that you can glide? Right? Are you going to reflect it horizontally or vertically? Okay. So for this one, it makes sense for you to reflect like this and then glide down, because if you imagine your reflection, if you reflect it horizontally, then you have B over here, C over here, A over here, and the orientation is not right. So you have to reflect vertically. So you want your A point to be the same at the same x, to have the same x values, right? So you want 1 as your x value, okay? That is the same height of your pre-image. Okay, so your middle point should be 1, comma, 4. Okay, does that make sense? Because you're getting 1 from A prime and then 4 from A. Okay, that should be your A prime or A prime prime if you want to say that's your A prime. Okay, and then same thing, you get X from B prime and then 2, comma, Y from your B, 2, comma 2. Okay, that's your middle point. And then you get X from your C prime, -1, comma, Y from your C, -1, comma, 1. C prime prime. Okay, so where are you reflecting your triangle? At line -1. Your point C does not change, does it? No, only after translation it's gonna be moved. But you gotta reflect at exactly x is equal to -1 line. And then you can glide down how many units? From height 2, you have to look at the y values. From this point, 2, comma 2 to -4, comma 2. Wait, no. I looked at a different one. B prime, your final image should be what? 2, comma -1. So look at 2 to -1. How many units are you going down? 1, 2, 3. 3 units. So what can you say? You're translating 3 units down, which is 0, comma -3. After you reflect across line, x equals -1. Okay, let me rewrite that. Translating 0, comma -3 after reflecting x equals -1 line for triangle ABC to end up with triangle ABC prime. Okay, that should be your answer for part A. What about part B? In the same way, you're just talking about a line, okay? Should I start a different color? Okay, line RS, -2 over 2, comma 4, that's R. S is 2, comma 6. Okay, and then you want to end up with 4, comma 0 for R prime. And then 1, 2, 3, 4, 5, 6, 7, 8, comma -2 for S prime. Okay, you want to have glide reflection. So look at your slope. Surely you cannot just translate it, right? Where are you going to reflect? Because your R prime ends up being higher than your S prime, you are going to reflect horizontally. You're going to reflect, yes, horizontally this time. And then you're going to glide down. So you want a point over here to be R and S to be over here, right? So that you can glide down. Oh wait, that is not reflection. So I'm gonna say your, oh yeah, I think that was fine. R to here, then S to be here. Oh wait, oh, we're reflecting horizontally. I'm sorry. So we're reflecting here to here so that we collide to the right right after reflection, because we have R over here and S over here. If we reflected across a vertical line, your S would be above and R should be down. Okay, so you need to reflect across horizontal line, which is going to be line x minus 4. This one is a harder one. If you find the midpoints and figure out the slope and figure out your y-intercept, you should get y equals x minus 4. Okay. Because why? Because your R, the middle point R, should be what? -2, comma, the same height, so 0. And S should be 2, comma, -2. Okay. So what are the midpoints? Midpoint of R should be -2 plus 4 divided by 2. That is your midpoint equation for your x value. And then your y values, you add them together and then divide by 2 again. So your R point is 4. Okay, wait. I did not use the right x value. You add the -2s because you have the same -2s, right? And then you have 4, and then what is that? 0, right? 4 plus 0 divided by 2. Your midpoint for R should be -4 divided by 2 is still -2, okay? And then 4 plus 0 divided by 2 is 2. So -2, comma 2 here should be your midpoint. Does that look right? Yes, it does, okay? Midpoint for S. We're talking about 2, comma 6 and 2, comma -2. Okay, we're finding the midpoint over here so that we find a line of reflection. Okay, so then we have 2 plus 2 divided by 2 and 6 plus -2 divided by 2. And that's going to be 4 over 2 is 2. 6 minus 2 is 4 over 2, so that's 2, right? So we have 2, +2, comma, +2. So looking at these 2 points, figure out the slope of these 2 points and figure out the equation of the line. The slope is 2, y sub 2 minus y sub 1. Oh, wait. And then 2 minus -2. And that's going to be 0 over 4. Oh, we do have a horizontal line. Okay. So what is the equation of the line? Your y must be 2. Okay. So that is going to be your equation for your line of reflection. Okay. So you have, after reflection, you have to slide down, slide to the right. How many units? From -2 to 4 is going to be a total of 6 units, right? So that's going to be 6 units to the right. So first we write a translation of 6 units to the right, comma 0. After reflection on the line y equals 2. And then you can say line RS, and that's gonna end up with line R prime S prime, okay? So let me circle and mark our answers. Those are our answers. Oh, all right. To wrap our lesson up, we had different types of rigid motions. We have reflection, translation, rotation, and glide reflection. The major thing, the new thing we looked at today was glide reflection. Okay, so again, glide reflection is what? A translation, a combination of transformations of translation and reflection, where translation is followed after a reflection, where the movement is parallel to the line of reflection. Okay. All right, that was lesson 4, classification of rigid motions. Bye.